Four movements in this chapter: the problem and the model, why least squares fails for a binary outcome, and how the logistic curve repairs it, interpretation and estimation through odds and risks, a worked clinical application, and extensions with the generalized linear model supplement. The goals: explain why least squares fails for a 0-1 outcome, write down the logistic model, interpret coefficients through odds ratios, relative risk, and risk differences, understand maximum likelihood, and estimate average risk measures in both languages. Binary outcomes are everywhere: a heart attack or not, employed or not, voting for a party or not, buying a product or not. And here is the observation that organizes the whole chapter in the box on the right. When the outcome takes only the values 0 and 1, its conditional expectation is exactly the probability that it equals 1. Any model of a conditional mean is therefore a model of a probability. So what goes wrong with least squares? Three things: out-of-range predictions. A linear function of the regressor can exceed 1 or fall below 0, while probabilities cannot. Heteroscedasticity. The conditional variance is the probability times 1 minus the probability, which depends on the regressor, so the errors are necessarily heteroscedastic. And linearity. A conditional probability cannot be linear in a continuous regressor unless the model is saturated. The municipal data make the failure concrete. Regress an indicator for being in the top income quartile on the tertiary education share and read the fitted line. At a share of 20%, it predicts minus 0.12, a negative probability. At 60%, it predicts 1.23. Both are impossible, and a model producing nonsensical probabilities is unreliable for inference and useless for prediction. The fix is to pass the linear index through a function that is bounded between 0 and 1. Cumulative distribution functions do exactly that by construction. Two are conventional: the standard normal, giving the probit model, and the logistic, giving logit, or logistic regression. Both produce very similar predictions, and logit is more common because its coefficients carry a clean odds ratio reading. The logistic function itself, the exponential of the index over 1 plus that exponential. It always lies strictly between 0 and 1. It is symmetric, so the value at minus theta is 1 minus the value at theta. It is S-shaped, flat near the extremes and steep in the middle, and it passes through 1/2 at 0, approaching 1 and 0 at the two limits. Substitute the linear index into that function, and we have logistic regression. Three consequences to note. The sign of a coefficient gives the direction. Positive means higher regressor values raise the probability. The magnitude cannot be read directly and needs a further transformation. The parameters cannot be estimated by least squares. We use maximum likelihood. And the fitted curve is an S-shape trapped between 0 and 1. With several regressors, the model extends in the obvious way, and the key line is the second. Holding other variables constant, a 1-unit increase in a regressor changes the log odds by its coefficient. Written the other way round, the log odds of the outcome, the logit, is linear in the regressors. Logistic regression is a linear model, but on the log odds scale, not the probability scale. Odds are the probability of the event over the probability of no event, and in this model, they equal the exponential of the linear index. Take the ratio of odds at two regressor values and the intercept cancels. The odds ratio is the exponential of the coefficient times the change, the properties on the right. Above 1 means positive association, 1 means none, below 1 negative. And crucially, the odds ratio does not depend on where you start, so a single number summarizes the association. Relative risk is more intuitive. The ratio of two probabilities, not two odds. It reads as the outcome being some multiple as likely. But it depends on the starting value of the regressor, so no single number summarizes it. When the baseline risk is small, the odds ratio approximates the relative risk. When the baseline is large, the odds ratio overstates it. The rule of thumb: they agree when baseline risk is under 15% and the relative risk is modest. The risk difference is the most directly interpretable of the three. The probability increases by so many percentage points. Like relative risk, it depends on where you start, and the cancer illustration shows why the three measures must be reported together. A rise from 0.05 to 0.07% is a relative risk of 1.4, 40% higher in relative terms, yet an absolute difference of only 0.02 of a percentage point. This table shows the odds ratio drifting away from the relative risk as baseline risk climbs. At a cancer diagnosis baseline of 5 in 10,000, the two are identical to 2 decimals. At a 5% baseline, they differ slightly. At a 25% baseline, the relative risk is 1.4, while the odds ratio is 1.62. The practical implication is stated plainly. Always report the baseline risk alongside an odds ratio, or it cannot be interpreted. With several regressors, both risk measures depend on all the covariate values, so we average over the sample. The average relative risk averages the individual ratios of shifted to original predicted probabilities. The average risk difference averages the individual differences, which is the average marginal effect on the probability scale. Both are consistent estimators, and the footnote warns that the ratio of average risks is not the same thing as the average of the ratios. Estimation rests on the Bernoulli likelihood. Each observation contributes its predicted probability if the event occurred, or 1 minus it otherwise, and independence multiplies those contributions. Taking logarithms turns the product into the sum shown here, which is far easier to maximize, and logistic regression simply substitutes the logistic function of the linear index for each probability. Maximum likelihood has no closed-form solution here. It is solved numerically by iterative, reweighted least squares. The estimates are consistent and asymptotically normal. Two practical consequences follow. Test statistics use the normal distribution rather than the t, because the theory is asymptotic, and confidence intervals take the usual estimate plus or minus critical value times standard error. Perfect multicollinearity breaks the estimation, exactly as in least squares. Model fit is measured by deviance, the likelihood analogue of the residual sum of squares. Null deviance belongs to the intercept-only model, residual deviance to the fitted one, and their difference is a chi-squared likelihood ratio test of the null that all slopes are 0. The information criterion adds a penalty of 2 per parameter to the negative log likelihood, so lower values indicate a better predictive model, much as adjusted R-squared did. The application: 303 patients at a Cleveland clinic who underwent coronary angiography. The outcome is a heart disease diagnosis. The regressors are resting blood pressure, sex, and age. And note the baseline flagged on the right. 46% of these patients have heart problems. That is a high baseline, which by the earlier rule means the odds ratio will not approximate relative risk here. The coefficient table, all on the log odds scale. Blood pressure, 0.0147 borderline significant. Male, 1.552 with a large statistic. Age, 0.0588, clearly significant. Below, the deviances: 480 null against 368 residual, a likelihood ratio statistic of nearly 50 on 3 degrees of freedom, so the three variables are jointly significant beyond any doubt. To make the coefficients readable, standardize the continuous variables by their standard deviations. One standard deviation of blood pressure, about 17.5 units, gives an odds ratio of 1.30. Being male gives 4.72. One standard deviation of age gives 1.70. And the caution repeats. With a 46% baseline, these odds ratios are not relative risks. predicting one specific case, a 50-year-old man with blood pressure of 140. Substituting into the fitted model gives an estimated probability of about 54%. And read the caveat carefully. These patients presented for angiography, a selected group, so this predicted probability should not be extrapolated to a 50-year-old man in the general population. Here are the three measures side by side for a 1 standard deviation increase in each variable. Blood pressure, odds ratio 1.30, average relative risk 1.14, average risk difference 5.5 percentage points, sex 4.72, 2.62, and 33 percentage points, age 1.70, 1.30, 11 percentage points. The odds ratios and relative risks differ substantially exactly because the baseline risk is high. When is the linear probability model acceptable after all? 3 cases. When the model is saturated, all regressors binary and fully interacted, least squares recovers group means, and predictions stay in range. When all predictions fall between roughly 10 and 90%, where the logistic curve is nearly linear, and when the target is the average risk difference, for which the least squares slope is often a good estimator. The recommendation: Logit for description and prediction. The linear model often serviceable for causal work targeting the risk difference with robust standard errors. The comparison in numbers. The least squares coefficients multiplied by the relevant standard deviations give 0.053 against the Logit's 0.055 for blood pressure, 0.33 against 0.326 for sex, and 0.108 against 0.112 for age. The linear slopes track the Logit average risk differences closely. Its advantages are directness and simplicity. Its disadvantage remains predictions outside the unit interval. The R implementation for the municipal example: read the data, keep the final year, build the top quartile indicator from the tax base quantile, log the population, then fit the generalized linear model with a binomial family and logit link. The formula interface is identical to least squares, only the family argument marks it as a logistic regression. Converting a coefficient to an odds ratio takes one line. Exponentiate the coefficient times the change of interest. Here, a 1 percentage point rise in the tertiary share. The confidence interval follows the same route, exponentiating both endpoints of the coefficient interval. Note the discipline embedded in the code. Build the interval on the coefficient scale first, then transform. The heart disease model in R: read the data, compute the standard deviations of the 2 continuous variables, fit the binomial model with the 3 regressors, then exponentiate the coefficients multiplied by those standard deviations to produce the standardized odds ratios of the earlier table. 4 lines reproduce the entire interpretation exercise. Prediction and testing in R: the predict function with the response type returns the probability for a specified patient profile, our 54% case. Below it, the likelihood ratio test is assembled by hand from the 2 deviances and the chi-squared distribution, with degrees of freedom equal to the number of slopes. Average risk measures in R follow the definition literally. Predict every patient's probability, copy the data, shift blood pressure by 1 unit, predict again, then average the differences for the average risk difference, and average the ratios for the average relative risk. Reading this code is the clearest way to see what those 2 averages actually are. And the linear probability comparison in R: ordinary least squares on the same 3 regressors, with heteroscedasticity robust standard errors from the sandwich package. The note beneath the code states the necessity: robust standard errors correct for the heteroscedasticity that is built into any binary outcome linear model. The Python versions begin with data preparation for the municipal example. Read the file, keep the final year, build the top quartile indicator by comparing the tax base with its own quantile, and log the population. The explicit integer conversion makes the 0-1 coding unambiguous before fitting the model. Fitting in Python uses the generalized linear model with a binomial family, whose default link is the logit, so the formula reads exactly like the R version. The odds ratio for a 1 percentage point change is again one exponentiation of the coefficient times the change. The heart disease model in Python. Read the clinical file, fit the same 3-regressor binomial model, then build a 1-row frame for our specific patient and predict. The printed probability matches the 54% computed by hand earlier, which is exactly the sort of cross-check worth doing once per analysis. Average effects in Python mirror the R recipe step for step. Predict on the original data, copy the frame and shift blood pressure by 1 unit, predict again, then print the mean difference and the mean ratio across all patients. Same 2 numbers, same interpretation, only the syntax differs between the languages. The likelihood ratio test and information criterion in Python. Fit an intercept-only model, fit the full model, take the difference of deviances, and evaluate it against the chi-squared distribution with 3 degrees of freedom. The information criterion is an attribute of the fitted model. This reproduces the statistic of about 50 from the coefficient table. 3 assumptions underpin logistic regression. Correct functional form. If the probability model is misspecified, the maximum likelihood standard errors are wrong, not merely inefficient. Independent observations or cluster robust standard errors when errors group, and no separate heteroscedasticity assumption because the Bernoulli variance is built into the model. The key difference from least squares is stated in the box. Logit standard errors are correct only if the model is right. They lack the robustness least squares enjoys. Beyond binary logit lie several extensions. Probit, swapping the logistic curve for the normal. Multinomial logit for unordered categories such as field of study. Ordered logit or probit for ranked outcomes such as grades. And classification, converting predicted probabilities into labels at a threshold, evaluated by the confusion matrix, the receiver operating curve, and the area under it. The first summary panel. The linear probability model gives out-of-range predictions and is necessarily heteroscedastic. Logistic regression guarantees probabilities strictly inside the unit interval. Estimation is by maximum likelihood with normal-based inference. The odds ratio is the exponential of the coefficient times the change, constant across regressor values, and relative risk and risk difference are more interpretable but depend on where you start. And the second, odds ratios approximate relative risks only at low baseline risk. Average both measures across the sample. Linear slopes track average risk differences when probabilities stay in the middle range, and fit is judged by deviance, likelihood ratio tests, and the information criterion. 5 discussion questions. The second is the one students most often fail. The odds ratio for being male is 4.72, and a colleague says men are 4.72 times as likely to have heart disease. With a 46% baseline, is that statement correct? The critical point, stated bluntly on this page, logit coefficients are not marginal effects. A coefficient measures the change in the log odds per unit increase, holding other variables fixed, and the log odds representation makes that linearity explicit. It is a log odds coefficient, useful for estimation, but not yet on the probability scale that interpretation demands. 2 routes take you from coefficients to practical effects. The odds ratio, exponentiating the coefficient, or the average marginal effect, averaging the coefficient times the logistic density over the sample, which lands on the probability scale. For sex in the heart disease model, that is an odds ratio of 4.72 or an average marginal effect near 33 percentage points. And the wrong statement is printed for emphasis. You cannot say being male raises the probability by 1.552. Logit against probit in practice. The logit uses the logistic curve, the probit the normal. The tables rows, slightly fatter tails for logit, a natural odds ratio only for logit, coefficients larger by a factor of roughly 1.8, and, in the bottom row, a practical difference that is very small in most datasets. The rule of thumb: logic coefficients run about 1.6 times probit ones, while predicted probabilities are nearly identical. Two summaries of the non-constant marginal effect are often confused. The marginal effect at the mean evaluates the derivative at the average of every regressor, which is easy but ignores heterogeneity. The average marginal effect averages the individual derivatives over all observations, which uses the actual distribution of the regressors and is the preferred measure. For the heart disease age coefficient, the two nearly agree, evaluated at the mean, where the predicted probability is about 46%, the marginal effect is about 0.015. Averaged over all 303 patients, it is about 0.014. Close here, but they can diverge when outcomes are rare or the sample is skewed. And the useful identity: the average marginal effect is the average risk difference for a one-unit change. Building a confidence interval for an odds ratio has a strict order of operations. Because the coefficient estimator is asymptotically normal, form the interval on the coefficient scale first, then exponentiate both endpoints. The closing instruction is emphatic: build on the coefficient scale first, then exponentiate, never the reverse. Applied to blood pressure with a one standard deviation change, the lower endpoint exponentiates to 1.20, the upper to 1.69. The 95% interval for the odds ratio therefore runs from 1.2 to 1.7, and it excludes 1, so the association is significant at the 5% level. The likelihood ratio test in detail: the difference of deviances between a restricted and a full model, distributed chi-squared with degrees of freedom equal to the number of restrictions. For our three predictors against the intercept-only model, that difference is about 50 on 3 degrees of freedom, overwhelmingly significant. It is the maximum likelihood analogue of the F-test, and it works equally well for comparing two nested models with different predictor sets. Logistic models can predict the event when the estimated probability exceeds a threshold, conventionally 1/2. The confusion matrix cross-tabulates truth against prediction, and two summaries follow from it. Sensitivity is the fraction of true positives correctly identified. Specificity is the fraction of true negatives correctly identified. Which matters more depends entirely on the costs of the two kinds of error. Sweep the threshold from 0 to 1 and plot sensitivity against 1 minus specificity, and you have the receiver operating characteristic curve. A perfect classifier passes through the top left corner. A random one follows the diagonal. The area under the curve summarizes discrimination. 1/2 is chance, 0.7 to 0.8 acceptable, above 0.9 excellent. Both languages compute it in one call. There is no exact analogue of R² here, but several pseudo-versions exist. McFadden's, based on the ratio of log likelihoods, where values of 0.2 to 0.4 already indicate good fit. The Nagelkerke rescaling bounded at 1, and the Cox and Snell version. None carries the fraction of variance explained meaning, so use them for relative model comparison only, never as absolute goodness of fit measures. Calibration asks a different question from discrimination. Do the predicted probabilities match observed frequencies? Group the sample into deciles of predicted risk and compare mean prediction with mean outcome in each. The Hosmer and Lemichaud test formalizes it. A model can rank well yet be badly calibrated, and the example makes the standard concrete. Among 1,000 cases predicted at 30%, about 300 should have the event. Calibration matters most when the model drives decisions. Two multi-category extensions in overview. Multinomial logit handles unordered categories by modeling log odds against a reference category. Ordered logit, the proportional odds model, estimates cut points on a latent scale and assumes a common slope across all cut points. Both generalized binary logit and coefficient interpretation is analogous, if more involved. The formula card in 7 rows, the logistic function, the logit as a linear model, the odds ratio, the marginal effect, the average risk difference and average relative risk as sample averages, the likelihood ratio statistic, and the odds ratio confidence interval exponentiated after the fact. 3 exercises. Build a bad air indicator from the pollution data and find where the linear model predicts negative probabilities, estimate a multi-regressor logit, and interpret its odds ratios against the baseline risk, and test whether a quadratic blood pressure term improves the clinical model. 2 more. Compare confusion matrices for the linear and logistic models on the municipal income data, asking whether the area under the curve agrees with the classification counts, and estimate the average risk difference and average relative risk for a change in wind speed, comparing that risk difference with the linear model slope. The practical workflow, first half, explore with scatter plots and grouped proportions and check the baseline rate, fit the linear probability model as a quick check of signs and magnitudes, fit the logit, report coefficients on the log odds scale with their standard errors, and compute odds ratios with confidence intervals. And the second half, assess the baseline risk to decide whether the odds ratio can stand in for relative risk. Report the average risk difference and average relative risk for interpretability. Check fit through the Deviance test, the information criterion, and a calibration plot, and state the limitations, sample selection, missing variables, and generalizability. Reading a full logit summary in R, the coefficient block with estimates, standard errors, and normal-based statistics, the 2 deviances with their degrees of freedom, the information criterion, and the likelihood ratio statistic, the dispersion parameter fixed at 1, standard for the binomial, and the iteration count 3 here, indicating fast convergence and no multicollinearity trouble. When a single continuous regressor is present, plot the fitted curve, bin the regressor, compute the mean outcome per bin, overlay the fitted logistic curve, and add the linear fit for comparison. 3 visual checks follow. Does the logistic curve stay inside the unit interval, as it must? Is the straight line a fair approximation where most of the data lie? And do the grouped proportions actually trace the S-shape? 5 pitfalls to close on. Reading an odds ratio as a risk ratio when the baseline risk is high. Building the confidence interval on the wrong scale. Comparing logic coefficients across models whose latent scales differ. Complete separation, where a regressor perfectly predicts the outcome and the algorithm fails to converge. And treating a predicted probability as a population estimate when it reflects this sample and this model. The remaining pages are an optional supplement placing logistic regression inside the generalized linear model framework, restating the maximum likelihood foundation and introducing deviance, the likelihood ratio test, and deviance residuals. The applied messages of the chapter do not depend on this material, but it explains why the machinery works. The likelihood, restated generally, unlike least squares, maximum likelihood adds a distributional assumption on the outcome, here the Bernoulli. The log likelihood sums each observation's contribution, weighted by whether the event occurred. And a reassuring special case, with no covariates at all, the maximum likelihood estimate of the probability is simply the sample mean of the outcome. With 1 covariate, substitute the logistic form and set the derivatives to 0, giving the 2-score equations shown here. They say the residuals sum to 0 and are uncorrelated with the regressor, echoing least squares. The equations are solved numerically. Very high multicollinearity can destabilize estimation, and complete separation can prevent finite maximum likelihood estimates. The generalized linear model has three components: a random component, the working distribution of the outcome, the linear predictor, and a link function connecting the conditional mean to that predictor. Inference is by maximum likelihood, exploiting the fact that the likelihood belongs to the linear exponential family, which includes the normal, Poisson, binomial, gamma, and exponential. Three examples show the framework's reach. The identity link with a normal working distribution gives the linear model. The log link with a Poisson gives the log linear model for counts. And the logit link with a Bernoulli gives our logistic regression. The logit is the canonical link for the Bernoulli, and probit is another common link for a binary response. Deviance compares the fitted model's log likelihood to that of the saturated model, one parameter per observation. The null deviance uses the intercept-only model, the model deviance the fitted one, and their difference is the likelihood ratio test that the regressors jointly explain the outcome, distributed chi-squared with degrees of freedom equal to the number of slopes. A final caution, and it is a real one. For continuous outcomes, both deviances are asymptotically chi-squared, but for binary or count outcomes, that approximation generally fails. It improves only with grouped data, where distinct covariate cells drive the degrees of freedom. Deviance residuals, which keep the sign of the raw residual but scale it by its likelihood contribution, are preferred over ordinary residuals for diagnostics and quantile plots.